didn't say that. It abstracts all computation in simple steps. And now, these steps are exactly 2 steps, which are very difficult to guess. The steps are map and reduce. So you have 2 sorts of operations, 2 sorts of primitives that you could use. One function called map, one called reduce. And if you studied Haskell before, I guess you'd be somewhat familiar with what map and reduce do. Right? So your computation proceeds in 2 phases. Okay? So the map gets as an input some data, right? It produces the data in a different way, right? And then the reduce acts on this data and sort of collects the information that you'd like to get. So for instance, think of counting the number of words in a huge file. Think of the word count application. Well, if you do the following, imagine each machine, if you imagine you have so many machines, but a very huge file. Imagine each machine counting the number of words per line. So each machine gets a single line. And it counts, it does the simple operation of counting the number of words in this exact line, right? Now this was sort of a map operation. You mapped like each line to a number, right? And now the reduce would do the following. It would take all the numbers and add them up, again in parallel. So for example, the first machine would get the first 5 numbers, the second machine would get the second 5 numbers, the third machine would get the third 5 numbers, and so on. And each machine would in parallel add all these 5 numbers together. And then you get some other numbers, and then you add these numbers, and so on. Right? So what the mapper really does, formally maps a key value pair to a set of key value pairs, or a set of actually, value pairs. And the reducer just aggregates, just like sort of combines the output of the map. It takes a single key and all the set of the corresponding values, and it does some operations on this set of corresponding values to produce a single value, maybe a set of values.
How do the PCs share the memory?
Well, they don't. The thing is, the thing with map is, if you remember in Haskell, maybe that's. If you remember in Haskell, if you remember having the map, for example, map plus 3, not very easy. If you remember mapping plus 3 to this list, like adding 3 to every single element of this list, right? So map would compute this function on every entry of the list. But again, each of these operations is totally independent of everything else, right? So you can do each operation so separately that you don't need to have to worry about like machines talking to each other through memory. That's what you have. So the 2 primitives are chosen wisely to have this property that you could do this work in parallel without having to worry about sharing memory. So they actually never share memory. Each gets sent its chunk of data along with the program, and this program executes on each machine in parallel, and at the end of the day, you get like different results on different machines, and then you collect those useful values.
Then it's not empty arrays.
Sorry? No, it's not empty. It's totally different from scratch.
So you said that each machine will operate in one line, get the sum, for example.
Yes. Yeah, one line was a simplifying example. So if you have a file, maybe this one, you have the file split into chunks, right? And you have some separate PCs. Like each chunk gets sent to this computer, right? And actually we'll see that nothing gets sent. This is the illusion. Each computer will compute and get a number on its own without having to share anything.
And then one will collect all both?
Well, maybe one reducer, maybe multiple reducers. It depends on the size of the data that you produce. Right? But now the idea is the following. Instead of sending the chunks of data to the computers, why not run the programs? So remember the file was split on different machines. So this, for example, was on PC1. This was on PC2. This was on PC3. Of course, along with other copies. Now, instead of sending the part on PC1 to computer, for example, 15, let's send a program that acts on chunk 1 to PC1. Right? So the data actually never gets sent that much.
Since you mentioned the file splitting technique in the file system, if I am showing that I want to count example, and each machine will take certain chunk of data for 12 months, how would you know that how to create or correctly split the file? I mean, that very much already.
Yes.
And so we'll be just
Okay, so his point is, his question is the following. Well, your question could be rephrased as how this works when the computation on different parts is interdependent.
yes.
Well, it will not work. You will have to redesign your algorithm to work in a way that is not interdependent. And the best example, one of the good examples, is the one they mentioned. If you're multiplying matrices, you could split the process of multiplying matrices into multiplying independence of matrices. You have to rethink your algorithm to fit the framework. The framework will not fit every algorithm.
Actually, the framework will limit you to take the input in a way that actually you take the input a chunk by chunk. Actually. You cannot access the whole file.
Yes, the framework is limiting you to take the input chunk by chunk.
So,
and the size of the data is actually limiting you to take the input chunk by chunk. Because at the end of the day, you're operating on things in memory.
also, the reducers will operate in the same way that it will take the key results chunk by chunk, so it can act and store the intermediate results on disk, such that the RAM does not get loaded. And as also,
the main point is the size of the data is prohibitive in doing anything else but taking the data chunk by chunk and processing them step by step and chunk by chunk. That's important. Yeah. So back to the map and reduce. So actually, the map reduce framework, as you might expect, works very well within the Hadoop stack. So you could, as I said, there works with HDFS and HBase. The big data that you're splitting, our procedures for doing that for HDFS files and HBase records are already written to you. So you don't need to have to reinvent every time you write a MapReduce job. So your MapReduce jobs on an HDFS will operate chunk by chunk properly in the way that it's expected to operate. And they work on the HBase, like several records by several records, in the way that you expect them to do that. So if you have a job that takes every record in HBase, does some computation at the end, gives you, for example, an aggregate value, like an average, a mean, or something like that, you could throw in the HBase table name, throw in your algorithm, and that's that. The whole idea is to abstract you from the internals of writing a parallel application. Right? So, as Mohammed said, probably at the beginning, he said at the beginning, that the framework of MapReduce, although it looks very restrictive, although it looks as if you don't have so much things to do, it's very expressive. You could express, I didn't see yet an algorithm that could not be expressed as MapReduce efficiently. Right? This is a very bold claim, but I mean algorithms that operate on large data. So you don't expect to be, for example, doing, I don't know, a Boolean satisfiability circuit program on huge input. You expect them to do something like analysis of logs, finding patterns, finding regular expressions, counting things, taking an average of things, and so on.
it especially works well with aggregate.
Yes. And if you're aggregating data, if you're taking so much data and producing a single value, or a single indicator, this framework will operate, would work perfectly. Okay? So at this stage, I'll finish MapReduce. I'd rather take a break of 5 minutes. Right? And so let's go on at 5 to 1 with the other parts of the